Okay, well, thanks everybody for coming. So, I will be presenting a paper which is a joint work with Nigel, where we came up with a method to basically distribute an elliptic curve-based protocol. So, before getting started, let me first motivate this work. So, elliptic curve protocols are extensively used in cryptography due to the security guarantees they provide. And so we have many cryptographic primitives based on elliptic curves, such as encryption and signature schemes. And in the other hand, distribution is a powerful property that one would like to have on a protocol because it has many applications, and besides having a secret key that is distributed among different parties will make the task for an attacker to compromise it harder than if it was only held by one party, and that's the main reason why it is so important to be able to distribute protocols. And so what we did in this paper is that we provided like a generic way to distribute any elliptic curve-based protocol, and we showed how we apply this to distribute Abe's mixed network. So we will see how we will do all of that in the next slide. And so all along the presentation you will be hearing multi-party computation. So before going any further, let me first give you a high-level idea about what it is. So multi-party computation allows a set of parties to do computation in their inputs without having to reveal them. And so at the end of this computation, the parties will get only the output of this computation and nothing else. And one big family of implicit protocols is called secret sharing schemes, which we'll be using in this paper, where basically every value inputted to the computation will be, each party will have a share of it. And so those shares are meaningless only if those parties will collaborate in order to use them. And so, so we will be distributing elliptic curves. So, what is an elliptic curve? Well, to build an elliptic curve, we need a finite field, and then we can consider an equation like this. And so the points that satisfy this equation will define an elliptic curve. And then if we augment those points with a point that we call points as infinity, then we can define a group law over those points. And you can see through the figure how we can graphically do this group law over the points. And in cryptography, we consider also the exponent group. So we have a group of points, and we take the biggest subgroup of prime orders of this group, and so we call this subgroup G, and then we consider the field that is defined by the order of this subgroup. And so from now on, when I say the elliptic curve, I refer to the subgroup G, and then the exponents group is the finite field Fp. And so our aim is to distribute computation over elliptic curves. So what computation we need to do over the points? So clearly we need to do the addition as defined in the previous slide, and also we need to do what we call points multiplication, where basically you take an element from the exponents group and x and that point over the elliptic curve, and x times q is just q added to itself x times. And also we need to distribute computation over the field. Why? Because to compute x times p plus y times p, of course we can do that only by the two operations defined above, but also we can do it by computing first x times y, then multiplying by p, which is faster. And so these are the computation that we need to distribute, and the strategy to distribute this is that for computation over the field, we will use a secret sharing scheme that uses Beaver triples for multiplication, and I will explain what does that mean in the next slide. And so, for example, we can take speeds, because speeds is a secret sharing scheme that uses Beaver triples. And for the rest of the computation, we will extend the same secret sharing scheme that we took over the field, and then we will extend it. And this is our contribution. How we can extend it so that we can get a protocol by which we can distribute computation over elliptic curves. And so to give you an idea about how speeds, well, it's a linear secret sharing scheme, and that means that inputs are additively shared among the parties. Space is actively secure with aborts, and that means that even if the parties deviate from the protocol, then honest parties they will catch this and then they will abort. Space is full threshold, and that means that even if there is only one honest party among the parties, then all the security guarantees will remain. And that means this party will always be able to detect cheating and then abort. And finally, speeds work in an offline-online manner, and basically computation takes place in two phases. We have an offline phase where some heavy computation takes place, and so we generate some data from the offline phase, and this data will be used in the online phase so that the online phase can be faster, can be executed fast. And yeah, so so to give you more details about how speeds work, well, as I said, value will be linearly secret shared among the parties. So party I will hold share xi from x. And then we need a form of authentication. We need a way to force, to avoid letting the players change their share of some value. And so in speeds we introduce what we call a MAC key. So it's a value from the field, and the authentication of x will be alpha times x. And so every player will hold as well a linear share of alpha x as well. And yeah, from now on we'll denote non-authenticated x as x between brackets with f as a subscript. And yeah, so that was the way we share points over the players. Now, how we do computation using them? Well, addition can be done locally, because if we want the players to compute x plus y, then we simply need them to add up their share of x with their share of y, and then the resulting value will be a share of x plus y. And also multiplication with a public value is also a local computation, because we simply need the players to multiply this public value with their share of the secret value. So as we saw, linear operations are for free because they are local computation. For multiplication, it requires communication, and we will see in the next slide why and how. And finally, so we have a form to authenticate values, but we need a way to use that. How can we use that authentication to check if the players they deviate or no? Well, when a value is opened, it's followed by a MAC protocol, and roughly speaking, this MAC protocol basically during this protocol, the players they compute the MAC on Z 2 times, one times with the shares they have they gathered during the computation, and then the second time by simply computing Z times their share of the MAC, and these two values need to be the same, otherwise a party has cheated. And it's actually hard to cheat, because if a party modifies Z, then it needs to force a MAC for the new value, and actually this can happen only with negligible probability, which is 1 over the size of the field on which we're working. And so, as I said, for multiplication we use Beaver triples, and Beaver triples, they are just triples of the form ABC, where A and B are random and C equals A times B. And so in speeds, we generate authenticated triple of these forms during the offline phase, and then whenever the parties they want to compute a multiplication during the online phase, then they can simply do this computation, and so they can get x times y by just doing this where there is only one round of communication. That corresponds to opening S and T in this protocol. And yeah, basically now we have everything to do computation over the field. And now what remains is that how we will do computation over the elliptic curve, and how to share points among the parties on the elliptic curve. Well, we decided to use the same a linear secret sharing scheme. So once again, a point over the curve will be linearly secret shared among the parties. And to authenticate it, we will use the same technique used in SPDZ. So we will consider a MAC key, and it has to be the same MAC key used for computation over the field. And then the authentication of a point over the elliptic curve will be the points multiplication of this point with the MAC key alpha. And then every player will hold a share of that value. And so, yeah, so from now on, we'll denote an authenticated Q as Q with between brackets with subscript E. And if we consider the secret sharing, then, yeah, if we want to do addition, then once again, it will be just a local computation for the same reason that 4 points over the field. Also, point multiplication between a public multiplier and the secret point, and multiplication between a public multiplier and a secret multiplier and a public point are both of them local computation, because we just need the parties to compute to multiply the public value with its share of the secret value. And for multiplication, the observation we made is that basically we can take one Beaver triple, remember the ones used for multiplication over the field, and we can map them to equivalent triples, and we can use those triples to do multiplication over the elliptic curve. And so how we did this, well, we take a Beaver triple over the field, and the players need to agree on a generator of the curve, and if we multiply the second and third component by this generator, then at the end we will have a triple where the first and second components are random. The first component is a point over the field, and the second is a point over the elliptic curve. And the third component is actually the point multiplication between the two first ones. And notice that this transformation can be done locally, because remember, multiplication with that public value is just a local computation. And then once we have such triples, we can do multiplication the same way we did it in SPDZ, by doing the same computation that will require one round of communication. And so the resulting protocol is a protocol by which you can essentially distribute an elliptic curve protocol. And the thing that I didn't define is the Maxcheck protocol, but we can easily define a similar Maxcheck protocol to SPDZ, and it will work for the same reason that made the one over SPDZ work. And notice that actually we didn't need to do any extra pre-processing. So basically we just used the offline phase of SPDZ to do computation over the elliptic curve, to distribute computation over the elliptic curve. And so in this paper we considered SPDZ, but actually this technique can also be applied to any Q to access structure, so it doesn't have to be full threshold such as in SPDZ. And actually not only computation over elliptic curve that we can distribute using this technique, because actually we can this technique can be applied to protocols over any finite abelian group of prime orders, such as the subgroup G of the elliptic curve. And yeah, so that was the protocol. Now in the paper we showed how we can use it to, we applied it on some trivial applications such as the ECDSA signature scheme, and also what we call or0 knowledge proofs. But as a non-trivial application, we considered mixed networks. And basically mixed networks are like a series of mixers, and they are used to break the link between messages and the sender of these messages. And mainly they are used to provide anonymity to those senders. And so in this paper we considered a mixed network, and a mixed network relies on uses a Waksman construction, which is in the figure here. And Waksman construction, like the building block of a Waksman construction, is a switching gate, like the ones here down, which take two inputs and they forward two outputs, and they swap them according to a signal bit. So if the signal bit is 0, then the switching gate will just forward those messages, otherwise it will swap them. And so yeah, so every switching gate, we associate to every switching gate a signal a signal bit. And before showing you how we distributed it, well, let's first see what is the task of a mixer in a mixed network. Well, the mixer first receives input messages encrypted using L-gamma, and the mixer needs to produce signal bits that correspond to a permutation that was drawn at random. And then in each switching gate, the mixer either swaps or not with respect to the signal bit, and also re-encrypts those ciphertexts because we need them to look differently. And to make this publicly verifiable, then the mixer needs to produce non-interactive zero-knowledge proofs, basically so that anyone can see that, check that indeed input messages correspond to output messages from the mixer. And finally, the mixer forwards messages, either to the next mixer or to the destination. And the approach we considered in this paper is that instead of having multiple mixers one after the other, well, we can consider only one mixer where all the mixers engage in an MPC protocol to emulate it. And so as I said, we took this as an application for our protocol because if L-gamma over elliptic curve is the scheme that is used to encrypt, then we can then use our protocol to distribute it. And that means we need to distribute re-encryption and decryption and the zero-knowledge proofs and actually any computation that involves elliptic curve points. However, the thing that still needs to be addressed is how to produce the random permutation, because an issue with Waksman networks that was addressed in a follow-up paper of the original one is that if you just generate the signal bits uniformly at random, this will not result in a permutation which is uniformly at random. And as you can see in this table that I took from that paper, well, some permutations occur more than the others. So this is the case where the mixer deals with 8 messages. So we have 8 factorial possible permutation, and 128 out of them, they can occur 32 times, but around 8,000 for them, they can occur only once. And this is not uniformly at random. And so what we did is that, so in the original Waksman paper, he provided an algorithm to transform a permutation matrix to signal bits. And what we did is that we distributed that algorithm. So we expressed it through MPC. And the main observation that we did that optimized a computation with that algorithm is that we can basically express that algorithm as a combination of linear equations, which are kind of easy to do with solve with MPC, and also quadratic equations that have a limited set of candidates to be a solution. And that was very so helpful in order to optimize the computation. And so the resulting, so we computed the complexity of this algorithm with respect to multiplication because that's the only operation that requires communication. And so as you can see, it grows polynomially with the number of messages. And so to conclude, so in this paper we constructed a method that we can use to basically distribute an elliptic curve-based protocol. This method can be also applied to any Q2 access structure that doesn't require, where the usage of max is not required. And actually we can use it to distribute any computation over a finite abelian group of prime order. And finally we provided a new approach to realize mixed networks by distributing one mixer using MPC. So that was all I had to say. If you have any questions.